the size of the obstacles or creating organizations that are trying to work around these obstacles rather than to remove them. So, and with those preliminaries, I will try and share my screen. All right. Good. And as we have also been talking, and Ulrich has been alluding to and saying very clearly, not just alluding to, that our publishing system, the point about journal rank, about Nature, Cell, and Science papers being so central, being the central problem, has been recognized for a very long time, already. But the problems associated with our publishing system, and with the publishing system, I mean the journal publishing system that covers all the fields that publish in journals. And in particular, very similar to Uli, I will be talking about experimental research, biomedical, psychological, chemical research. These are the fields I will be covering, and those are the ones that are being published in these journals. These issues with these journals have deteriorated to an extent that now I will try to make the argument that they are the biggest threat that we're facing for publicly funded science today. Now, what do I consider a threat? A threat would be that when you read a headline about science that says, when you hear a scientist talk about peer review, you should reach for your Browning. And of course, peer review is what happens at these journals. And this, for all of those who don't know what a Browning is, a lot of my students don't know that this is a Browning. And the quote comes from a German play called Schlagetter that was shown for the first time on Adolf Hitler's birthday in 1933. And the original quote says, "Wenn ich Kultur höre, entsichere ich meine Browning." So this was a riff on a Nazi play, on a Nazi say, that essentially, if a scientist talks about peer review, that scientist should be shot. Now, who has been saying that? It was the outlet where it was published was the outlet of Steve Bannon. This is someone who's probably quite well known by now to most people. And you might say that, well, this guy was only in the White House very briefly and is really just some crazy nutcase. Clearly, nobody in high places would ever think that sort of way. But of course, as you probably also know, Trump suggested to cut a lot of the science budget. He didn't get through with his proposals, but that's beside the point. The threat here is that there are numerous Trumps all over the world who seek big cuts to science funding for reasons that are probably obvious to everyone around here. And it's ever only an election cycle away that some of these people get into power. And it's ever only just another vote in some parliament away from actually succeeding. And people have, long before Trump got elected, people in his group, so to say, have, here you can see it in 2017. Actually, that was after he was elected, but it was before Rick Mulvaney became Office of Management and the head of the Office of Management and Budget, have asked whether we really government-funded research at all. And why? Because in this case, Zika science is so uncertain. So Zika, the infection, if you remember, the infection that happened before the SARS-CoV-2 pandemic, shouldn't be funded. And so it's this reproducibility that's being used as political ammunition to stop and cut and at least reduce science funding. And as publicly funded scientists, I would argue that the biggest threat to science is the threat to stop funding it because the science is not, or is perceived as not being reliable enough. Where does that come from, that idea that science could not be reliable enough? Well, this is not a new idea. This is from 2013, How Science Goes Wrong, a big title on The Economist. So it was not in a scientific journal. The scientists have been talking about this much earlier than that, right? The BBC News writes in 2017, most scientists can't replicate studies by their peers. And then it says nearly all of our medical research is wrong. I would say that probably most people would disagree that this might be a slight exaggeration. Things might be bad, but probably not all that bad. But how bad are they really? And now I will draw on the data of the people that I talked about before who have a different approach to these problems, who try to find out what is the scale of that problem. And this definitely doesn't hurt to know the scale of the problem, that's for sure. And there was a publication many years ago now that summarized different kinds of reports. And what you see here is reports that looked at materials and methods studies and assessed, well, from the way the authors have described their experiments, how reproducible will these experiments be? And they came up to something about 50%. These are reports from companies, so we can't scrutinize them, of trying to replicate experimental research, and then they couldn't, to 90 or 80%. All of these studies have the problem that they can't be checked. These three here on the right are theoretical studies, and these three are closed. We don't know which experiments were done and how, because the companies won't disclose that. And so people have started to do, and especially spearheaded by works from Brian Nosek at the Center for Open Science, to do reproducibility experiments in a very rigorous, controlled way. And what they find is indeed something that's in between these early predictions of about 60%. So we'll stick with this roughly, 50%, 60. We'll be a little bit more optimistic than the open science collaboration here and say, okay, this is about 50% is what they find. And this is in psychology. So now one might say that psychology is a particularly unreliable field with a lot of variables that are difficult to control and all of these things. So let's look at other fields. Social sciences, there now we also have reproducibility experiments in really high-profile papers or high-profile results published in high-profile papers. And what they find is, again, something like 50%. In this case, this is a successful percentage, 60%, a little bit over half. In economics, people have done that too. Again, here also about 60% successful, 11 out of 18 studies that people have tested here. Most recently, most close to me as a biologist, even though I do neuroscience, is cancer research, where there is at least some biology in it, even though most of this could probably be termed medical research. And here, the people tried, and this is again was done by the Center for Open Science. In the initial design, they selected 193 experiments. And then they did what the people in the very first graph tried to do. They looked at the methods section and tried to find out, okay, is this really reproducible? And then you can see they looked at whether the data was shared, the analysis was properly reported, code was shared, reagents offered. They even talked to the authors. So after all of this was done, out of those 193 experiments, 87 could actually be started. Now that point alone, that transition alone, to me, if I would have ever done 193 experiments, I would hope that 193 experiments could be done. I would probably resign and say that I took the wrong job if only 87 of my 193 experiments could even be started to be replicated. But out of those 87, they couldn't even finish all of them. Only 50 could be finished. So 193 experiments were attempted, 50 could be finished. So that alone, irrespective of outcome, is an indictment of this field and seems to match what one finds in other fields. In total, 23 papers, 50 experiments, 158 effects, 188 outcomes. What's the result? You can see each individual outcome here. In blue, it was less than a 0.05 threshold. In red, higher than a 0.05 threshold. The original effect size you see here is dominated by large effect sizes. The replication effect size here is very obviously much, much smaller. You can see the distributions here that are much more narrow, around 0. Success rate was 46%. So we're again in this 50% range. So it appears, looking at many, many different fields in selected experiments, about 50% of what we do is reproducible, and the other 50%, for various reasons, as you could see here as an example, is not reproducible. Now, what does that have to do with journals, right? Because this was done in much of this work was done on experiments that were published in high impact and prestigious journals. So the question then is, okay, this is really just a small percentage of the publications is in these journals. Is the rest of the literature more or less reliable than these 50%, which are already from my own, for the kind of ambition I have for my own research, very, very low. So is it even worse in the rest of the literature, in the remaining 92% or so of the literature? And that appears to be not the case. In fact, the opposite appears to be the case. And I will show now just a very few, for time reasons, a very few examples of a large body of literature where people have looked at exactly how well experiments have been done that have been published in various different places. So this is an example. This will be 2-3 examples out of different fields. This is a field, a biochemical field, crystallography. So you shoot X-rays on crystals to find out which, mostly biological, but also some more chemical structures, and then find out how do those structures look. And every single little dot that you can see here in black or in blue or in red, every single little dot is such a computer model for such a structure. And they're all sorted by their different journals here on the x-axis. And the y-axis is a quality measure. So what they can do is they can take the computer model and take a lot of different factors and calculate a quality metric out of that. So one of those factors, for instance, is, does the atomic distance between two atoms match the one that it has to be according to what we know about these atomic distances? And so the further away they are from this ideal or this true distance, the more of a penalty they get, which means that this quality measure is 0 if it's perfect. So there's no difference to a perfect from a perfect model. And what they have done here is they have taken all of these values and set the average to 0, such that everything above 0 is worse than average, and everything below 0 is better than average. And then they computed average values for each journal that publishes these structures, and then ranked them and ordered them here according to this quality metric. And everything that has an asterisk or a color is significantly different, and in red worse than average, and everything that is blue and that has an asterisk is significantly better than average. And what one finds is the highest ranking journals like Cell, Science, we have Nature here, EMBO Journal, PNAS, all of those journals are in fact worse than average. So so in terms of reproducibility, if one wants to reproduce the actual structure, the higher ranking journals do a worse job than the lower ranking journals. A different field, this may be typical to structural biology or structural chemistry, simply because everyone is racing towards these structures, and so they work sloppily, and this is not really something that's a big problem, one could argue. And so let's look at a different field, and let's look at statistical power. Statistical power should be of experimental designs should be above 80%. That's the convention, and this is data from experimental neuroscience. So this is more or less my field where I work, but I don't think any of my studies are in there as far as I know. And each individual dot is one particular experiment and the actual statistical power that it has. And as you can see, there is no relation between impact factor on the x-axis and statistical power on the y-axis. So a quality experiment would be in this range, and you see it covers the entire range. And even the highest, let's say 3/4 in this case of the highest ranking experiments do not meet the 80% statistical power criterion. So again, there is no evidence here that the top journals are in any way better, and in this case, also not worse than the rest of the journals. Another issue that comes up, and again, a different field, is mistakes that happen, errors that are not checked for various reasons. And this is bioinformatics. And what people in bioinformatics often do, they get lists and lists and lists of genes out of their applications that they program and code. And then they, for publication, they paste them into Microsoft Excel and submit them with their articles. And because Microsoft Excel has sometimes issues and misreads gene names to dates, the problem was found to be so pervasive that scientists have started to rename human genes so that this problem would not happen anymore when people use Microsoft Excel to publish their data. This is quite funny. I find it quite funny. The data seem to suggest that this is something very common. What you see here is the overall average of the studied papers, and about 20% of papers with these data in Excel spreadsheets have this issue. And what you see here is ranked, again, journals, and how often this happens in these various journals. And if you take the impact factor of the journals that are worse than average, so have more mistakes than average, and you take the impact factor of the journals that have a low, that are below the value of the average percentage of mistakes, then this impact factor, the average impact factor, is higher than this impact factor. So again, here it appears that there are more errors, so which means less replicability in the high impact journals. And those are just 3 examples out of a whole range of different, or a whole body of literature over the last 10, 15 years that all point into this direction, that replication, replicability, quality, sloppiness, or the inverse of sloppiness, is worse in the high ranking journals. So the high impact journals, they seem to attract, for some reason or another, and then publish the most unreliable research. So you don't need to be an evolutionary biologist to realize that if you hire people by publishing in these journals, then it's probably not going to be a surprise if you do this for long enough, then you will come and have a replication crisis simply because you keep hiring people who do more unreliable people than those that you're not hiring, that publish more unreliable science than the people that are not being hired. Reliability, however, of our literature is only one of the problems that our literature has. And the other 2 problems that I'm going to briefly mention now, the other 2 problems are connected to it. And that's why I think it's very important to mention them. This trinity of failures, if you will, contributes to what I would call a crisis in our infrastructure, which I think is, if Ulrich Dirnagel is right, that or this infrastructure, this part of the infrastructure, this journal system sits at the center of our problems, that this crisis goes so deep that I think fixing this is probably the very, very first thing we ought to be doing if we want to avoid the threat of defunding of publicly funded science. The affordability problem is the second issue. Things have become very, very expensive. So the higher you publish does not only mean the more sloppy the work is and the less reliable it is, it's also more expensive. So you pay more for lower quality work. Nature APCs have now risen for over, if you include taxes, for over 10,000 euros. Here the recent, from 3 days ago, the recent announcement by the Nature community journals that if you just publish Nature Neuroscience, it's not Nature itself, and any other community, Nature Ecology and Evolution, these sorts of things, it's 9,500 euros plus tax. So that amounts to something like 11,000 euros or something. Now, one has to keep in mind that their costs of publishing this are much, much lower. Now, this is not the cost of publishing a Nature Neuroscience article. This is the cost of publishing a generic article in one of the publishers that I have listed down here. right? And some of these will have a little bit of a higher value, some of it a little bit of a lower value. For instance, CLO publishes in the global south, so they will be more close to this lower value. Some of those, many of those publish in the $400 range, and some go up to maybe $500 or $600, but that's already at the upper range. So the costs to publish a generic article are between $200 and $400, $500, $600 US dollars or euros, roughly. And maybe for a very, very selective journal, such as the Nature journals, it can be as expensive as about 1,000 euros. So those are about the costs. So even for the highly selective Nature journals, they charge 10,000, 11,000 euros, but their actual costs are only about 1,000 euros. So if we take a generic article, right, not a high-profile journal, then a generic article on average, one can calculate these numbers quite precisely, and they've been fairly constant for quite some time. The price range for a generic article is about 4,000 to 5,000 US dollars. And if we take the charitable view of for the publisher's charitable price of about $4,000 and a very high range of the costs of about $600, and then the publicly stated profits that they make for each article of about $1,200, there remain about $2,200, more than half of non-publication costs. So of costs that happen that have nothing to do with publication. So that have to do with executive pay, with lobbying efforts, with acquiring technology, with paywalls, all of these things that have nothing to do with publishing. So on average, more than half of what we pay publishers does not go to either publishing or profits. It goes to something completely different. Now, what could that be? Elizabeth Bick is very well known for her talent of spotting image duplications and manipulations, and is quite famous in the reproducible science community. And she wished that it would be nice if scientific publishers could be spending some of the millions of dollars we pay them on hiring staff to screen manuscripts for errors and fraud, and to quickly deal with concerns raised about published papers, like decent quality control. So she would like to have, if she finds an error, she would like to have someone at the journal where she found the errors who would follow this up and fix it. And that doesn't really exist. Why doesn't that exist? Well, because they pay the publishers use the money that we give them for something else. So some of the non-publication cost goes into spying on users. So if you go, depending on how and when, and from which location you access, let's say, a Nature article, this Nature article, you're being tracked by 21 different pieces of software, or by 34, or by 73, or by just 2. So over the course of the last 10 years, one of the things that the publishers, and this is just one example, right? You can check this with a browser plugin. You can check this for any of your favorite journals. They track what it is that you're doing on their sites with the literature, with our literature that they host. And of course, they don't do this for commercials because they get subscriptions and APCs. They don't need to use this for advertising. No, what they do, of course, is one aspect of what they do. I'll show you another aspect soon. But one aspect of what they do is they sell the data so that it can be combined with your private browsing, such that when you're privately browsing on some site, you can get some advertisement to maybe subscribe to a personal Nature or buy a personal Nature subscription or something like this. And so be aware, if you're browsing on a publisher site and you have your cell phone in your pocket in the same university network, then most likely your private data on your phone and your public data or your work data on the publisher side will be combined at some point at an aggregation service, either one that the publishers are now also running, or an aggregation service that has just bought your data and combined it. This is a major issue. The DFG has picked this up, and in particular in Germany, this is an issue because academic freedom is part of our constitution. And if you want to know how this practice by publishers infringes on your academic freedom, I can recommend reading this article, this paper. It exists in both in German and in English. This contains a lot more detail than I have time to go into now. So where do they track you? Well, they track you on their publication sites, right? You see that here, Cell Press and Nature and all of these, Wiley and all of these things, right? This is what they have, and where they have the trackers that I showed to you. But already 10 years, more than 10 years ago now, for instance, Elsevier bought Mendeley, where you can find literature and that you use when you cite literature. And they have bought other tools. This is what they use your money for, such that all of these big four publishers, they now cover most of the research workflow from discovery, analysis, writing, publication, outreach, and assessment. Which means that if people are using these tools, then Elsevier knows what it is, what kind of research you're looking for, or Holzbrink. They know what data you have and how you analyze it. And when you're writing your manuscript, they also know what you're writing about. If you use Overleaf, then Holzbrink knows what the paper is that you're currently writing and could, in principle, suggest to you where to submit it, even before you're done with it. Of course, I don't need to talk about the publishing. And then via outreach and assessment like Nature Index, Nature Index also ranks your university. You can go to Nature Index and check how does it rank your university. And the reason why it can do this is because Holzbrink covers the entire workflow and knows precisely what it is that you're doing, and could, in principle, at one point, if they want to, sell your university leadership a package that covers everything, such that we don't need to have committees anymore on who gets hired or who gets fired. You can get algorithmic employment decisions, and this is something that is already happening in certain, not in academia yet, but in other places, that people get fired if they trigger certain algorithmic misdeeds that they should not be doing. So this is something that the publishers have invested heavily in, to an extent that Elsevier now no longer considers itself a publisher. You can go to the Elsevier website and look. The only thing that you will be finding is that they say Elsevier is now a data analytics business that has its roots in publishing. So publishing really, because we have been financing them so well, publishing really isn't one of the major issues for these institutions anymore. It's now data. It's your data. These corporations, formerly known as publishers, are now data analytics businesses, and we provide data for them and pay them for it. But as you could see here with this research cycle, we don't only produce papers, right? We also have data and code. So if we already saw that impact analysis is not so great, quality control is not so great, there's a lot of lists. I'm not going to go into this. And everyone can have a look at this list at their own pace. But there's many things that are wrong with our literature because the publishers have spent their money elsewhere. They don't care what's in the literature as long as we pay. And we have kept paying way beyond inflation for the last 30 years. So there's no why. If we keep paying more every year, why should they change anything in the literature? Why should they improve anything if we keep paying anyway? So it's no surprise that in the last 30 years, there's been a lot of accumulating issues with our literature, technically speaking, which adds to the functionality crisis, which is the third crisis after the affordability crisis. And you see how it is connected. So the functionality crisis is connected to the reproducibility crisis via the affordability crisis, because without money, we cannot invest in mitigating effects to make sure that our quality control of the literature and of our work is improved. All the money that we could use for that is flowing towards publishers and their own goals. Data infrastructure is also bad. This is a very old, by now, an 11-year-old study report on the integration of data and publications that finds that There's a very small proportion of data that is relatively stable and accessible. Most of the data is on disks and in drawers. But even the stable data is not what I would call stable. And this is also an old problem. This is a screenshot from a database, proteomics database from 1996. So you see these databases have been around for a very long time. SwissProt should have been 10 years old in 1996. So this database exists since 1986, but it has funding problems. This is an infrastructure, unlike the electricity and the internet that is powering what we're doing right now, which is not funded by project funds. Many of these databases where probably the most important product of scientific work is being taken care of, scientific data, many of these databases are not funded by infrastructure funds, but by project funds. And if the funder decides they don't have any money anymore, then these databases go extinct. This is not something that has gotten any better. In 2016, funding for key data resources are in jeopardy because the NIH doesn't have any more money. And the consequence of that is that the availability of research data declines with article age. So the older, because databases break away and because publicly accessible data then becomes inaccessible, the older the publication it becomes, the less accessible the data is, even if it has been there at the time of publication. Now, you might have thought that that the situation with the infrastructure for text is already pretty bad, and for code and for data it's even worse. But for code there isn't even anything. So researchers have been sharing and reusing each other's software and code since 1953. This is the first computer for which code sharing has been documented. So now it's 2022, and we still do not have institutional support that helps us do this task of sharing and reusing software and code from each other. It just simply doesn't exist. No institutional value of it. What exists is something called GitHub. This is probably at least the third or fourth iteration of websites, essentially, that help any coder, not just scientists, any coder or developer to share code. Microsoft has recently bought this, which is an issue because Microsoft is in the habit of just shutting stuff down that doesn't make any profit. For instance, Microsoft Books. If you ever owned a Microsoft book, you don't own it anymore because they closed it down and took all their books with them. So this has been widely publicized. And if you have any code on GitHub, be prepared that this might happen to your code as well. It may be gone tomorrow, simply because when Microsoft finds it's time to take GitHub offline. So I was very happy when, as the pandemic started, a lot of digital innovations that people have been calling for a long time suddenly became possible. And in this case, the Uni Regensburg, my institution, installed a local repository that helps share and make available code called GitLab. So this is the same Git technology. And I was very happy and I said, oh, excellent. I'd like to have that and always mirror it with our GitHub repositories that if GitHub goes down, I still have the GitLab version. But I couldn't find where, I know this is possible, but I couldn't find the settings where I could set this up. So I contacted the person who was in charge, and they replied to me, and this is in German, so I've translated it, that, we have installed the free version of GitLab, in which pull mirroring with GitHub is not included as a functionality. So again, because we pay the publishers so much, we now can't use the GitLab that we have to conveniently mirror it with GitHub, where we actually work and we actually share our code. So again, a very local, very recent and up-to-date example of how these different functionalities interact and how they all are connected with the issue of journals and journal rank. So because this is the core problem, I would argue that one should tackle the reason for the problem. Just like if you know the cause for the disease, you should get rid of the cause and not treat the symptoms. Now, we said that an article costs about 4,000 to 5,000 euros or dollars. Now, for this example, I just picked the 5,000 number. It's probably somewhere in between. And I picked the lower bound service number. So if we buy content, as in subscriptions, we pay about 5,000 per article. If we pay for a publication service, we pay about 200, let's say, dollars per article. Now, given that we publish anywhere now almost exceeding 3 million articles a year, at this point, it wasn't at 3 yet when I created this figure. But if we calculate with 2 million articles, it's going to be more. With 3, then we have about 9.56 billion every single year. If we switch our system from the current system that costs us 5,000 per article to a service-based system that already exists, it doesn't even have to be built. We just have to implement it. It's there. So if we use that,
just a quick reminder that it would be great to have some time for questions.
Yeah, no, this is one of my last slides.
Thank you very much.
I think I have 2 or so more slides. And so this system, if we had it, would afford, so if this money, if we saved it, would give us 9.5 billion per year. And just as a reference, because I don't know what 9 billion buys, the International Space Station to build and maintain costs about 3 billion per year, and the Large Hadron Collider about 2 billion per year. So just so you have an idea of what kind of money we're giving publishers that doesn't give us anything back. On the contrary, it's really hurting science. And what could we get for that? Well, if we have this system, we could substitute the service providers, just like we can substitute the email providers, and the universities routinely do, and usually we as users don't really notice this. The authors wouldn't have to pay anything. If we want to copy any functionalities from the journals, we can do this. We don't need to force anybody to use this, and so on. All kinds of advantages, save a lot of money. Now, I said this already exists. One example is something called Open Research Central. In Open Research Central, you just have one place where you browse articles, where you can find your literature. And the only thing that one has to do is to hook up one's publication platform. So every institution, let's say you don't have journals anymore, every institution publishes their own papers according to peer review, the way we do it now, right? We do peer review now with our own editors and with our own peer reviewers. So you do it in the same way. It's only the physical place where they're deposited is different. Everything else runs the way it runs before. Open Research Europe has done the same thing. And so you hook all of these institutions and their platforms up in the same place. And you have one place where you can get all the text, all the data, and all the code. And because this is so much cheaper, there's plenty of money left over to make sure that this will constantly develop and increase and get better. The effect of that is that we have our literature will be dynamic and version controlled, can be searched and text mined all the time, all of these things that we can't do now. Publication is near immediate. When everybody is agreed to publication, it will be there. Different models for post-publication review exist. We can do whatever we want with it. We can have contributorship in diverse roles, not just authorships. We can make sure that data and code deposition also count, not just publications, and so on and so on and so on. Now, how could we get institutions? And that's the last slide. How can we get institutions to stop paying a lot of money for something that's bad for science and invest a little of that money in something that's actually going to be good for science? Clearly, this has been possible for many, many years now, but they haven't done it. I would take that as evidence that they don't want to do this or can't. In either way, they need some incentives. And so I would argue, and we would argue, that the incentives should not be on the authors, because we authors don't really have any power. The incentives should be on the institutions. And what institutional incentives do we have? Well, and here's just a list of funders. Every funder has a list of things that institutions have to comply with if they want to have funding. So if we have Ulrich Diernagel's or Center for Open Science, but the one that Ulrich Diernagel was talking about, if we have the top guidelines for institutions and they incorporate, transparent and open science practices, only then, if we can incorporate those into the eligibility criteria, then all the institutions would make sure that they conform to those criteria, because otherwise they would not be able to get funding. And so this incentive would really get something going, where the infrastructure would massively change and where institutions would get an incentive to take the money away from the system that hurts science towards the system that benefits science. And once the infrastructure is automated, then the incentives are gone. The teaching doesn't need to be so intensive, because the infrastructure rewards openness automatically simply by making it the default. And with that, I stop the screen share. Thank you for your attention. Oops. Thank you for your attention, and I'm open for any questions, of course. Thank you.
All right, thank you very much. That was very interesting. I didn't know about very many of the things you said. Are there some questions directly? Or some statements you want to make, Daniel?
I want to agree with the general gist of it, that we basically need to replace the for-profit publishing model by a non-profit public option, which seems to me what you're arguing in favor of. Just one thing, wouldn't we basically acquire quite a bit of a redundancy problem with having every institution getting every institution involved in publishing their own stuff? Wouldn't it be much better to centralize this, as the ZPID, the Leibniz Center for Psychology, is doing?
That's a good question, and this is still an open debate pretty much. I would argue that the redundancy in this case is actually an advantage, right? So one of the problems, for instance, and here's an example why this is an advantage. One of the issues with the fickle databases where our data sits is that one of the most stable databases and one of the most important ones is for biomedical research is the NIH databases that are funded by the US government. And if the US government shuts down, however, it has been in recent history been very close to also shut down those NIH databases, which would essentially mean that most of biomedical research on this planet would stop. And this is one of the most stable databases possible. But it's in one single place, it's at the NIH. And so I would actually argue that if we had a decentralized backend where, if you have authors from 5 institutions that write one publication, and each of those institutions has a copy of that. And if you formalize this, for instance, with a peer-to-peer backend in the file system, or IPFS, right, file system, then what can happen is a natural or political catastrophe can happen in, let's say, 1/3 of the planet, and the remaining 2/3 still have 100% of the content available. And so for these reasons of robustness and resilience, I think the decentralized model would actually be superior. There's also, and with this I will conclude, I will only give 2 reasons. The other argument is financially. Is if you have local control over your infrastructure, it means that you can have local tenders, and you could actually have local businesses compete with the big businesses to do the technical tasks, right? To run the servers, either to host them servers, or to do the software maintenance, or to do training, or to do services such as support. And the institutions themselves, then the libraries and other infrastructure units can decide, okay, do we want to do this ourselves? Do we want to outsource it? How much effort and money do we want to put in where? And so I think from this perspective, and of course, each author and each researcher has local people to talk to if they run into problems. And so those are the 2 reasons why I would argue for a decentralized system. But there are, of course, trade-offs to be made. And experts who have more experience in this probably should get together and decide whether decentralized or centralized where the cost-benefit analysis comes in.